Welcome back. Now we're going to look at the concept of aromaticity using all three criteria for all three of these molecules shown on the screen. I apologize for the quality of the molecule itself. For some reason, it looked really better on the screen when I actually constructed it than when I transferred it onto the screen capture. So the question says, determine if the molecules are aromatic or not. Your easiest bet to do would be to first do Acos Rule. And if Acos Rule is obeyed, then go back to the other two criteria. So let's just pick this first molecule, okay? So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pi electrons, okay? Again, I'm only going to focus on what's inside the ring, right? Now, can we get the 10 pi out of the 4n plus 2? You sure bet. If we put n equals 2, plus 2 equals 10, so yes, Acos Rule is obeyed. So I'm going to call it HR is tick, means it's done, it's obeys. Now the question of whether we have alternate double, single, double, single, double. All right, I'm going to use this for double and use this for single. Okay, so this is double, single, double, single, double, single, double, single, and then double here. So single, double, single. If you notice, there is at no point this is followed by a double is followed by a double, or a single is followed by a single symbol, right? I'm gonna actually delete that because I don't want it to cloud my screen. So this is my coding. If you notice, throughout the entire process, all I have is a double, single, double, single, double. So if I call it D/S, that is also obeyed, right? That's the second criteria. The third criteria is resonance. I'm going to actually redraw the molecule so I can actually explain it with different colors. And you might just be able to do it for the remaining molecules yourself if you want to pause the video after I explain this, okay? So I'm going to get a different color. So when you have a benzene ring, okay, you can move this molecule, okay? This is in this ring, right? Now, if you do traditional, like here, like we did for Diels-Alder, you probably will end up with 2 double bonds and you wonder why. It doesn't work just like that. So if you take this molecule and move it here, and you move this here and here, okay? Now, if I redraw this molecule, I'm going to draw the structure, actually, sorry, structure in blue, so I can show the bond movement in red. Now, if you find this harder, hopefully by the time we do a second molecule, it will make more sense, okay? So now let me get my red, and you notice you can only move one ring at a time, okay? You cannot do the entire molecule like you do your Diels-Alder, okay? Don't do that. It probably will never work. Now, if you notice, this is not same. This is how this molecule looks like. Now, this molecule looks like it. So all you have to do is pick the ring where it contains all 3 bonds, and pick the one that's adjacent to the next ring, move it into the second ring, and if you do it, this right here, folks, is a resonance structure of this one, where the triple bond was, the 3 pi bond was in this ring, now it's over here, right? Now that's all you can do. You don't have another ring to go further in the chain. Okay, so we are able to reproduce from one structure to a newer structure, so resonance is also obeyed. So that means all 3 rules are done, so this is aromatic. Okay, now I may not be able to do this one in lieu of time, but it's basically, if I explain this to you, you should be able to do this, right? So let's go ahead and do our Acos Rule for this one. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And in other words, we have 3, 5, 7. 7 pi bonds is equal to 14 electrons. So can we ever get 14 electrons out of this 4n plus 2? Yeah, sure. If you put 3 for n, you'll get 14. So that means Acos rule is obeyed. So HR is done. Is there, again, double bond is this symbol and single is this. So I'm going to start here. It doesn't matter where you start. Double, single, double, single, double, single, double, single, double, single, double. Well, if this is single and this is double, this has to be single, right? And then double, single, single, double, and single, right? These are not adjacent to each other because you may think, hey, that was single next to single. No, that's not the case. It's just that this is a connecting bond, so it would have to be single, or it could be double and single. Either way, we are able to get double and single throughout this molecule. So D/S is, if you think about it, if this is confusing to you, this is not confusing, right? Double, single, double, right? Or double, single, double, double, single, double. Either way, if you think this is confusing to you, which I just pointed it out, I'm going to erase that again. Think of it this way. This is double, single, double, right? This idea of two single bonds here might be confusing to some of you. That's because this is a ring connecting bond. And that's not wrong, okay? This is correct, right? So this is done. Now the idea of resonance, right? So I'm going to redraw this molecule the way it looks like in its original form, okay? And as I said, you can only move into one ring at a time. You cannot move through the entire molecule, which could lead to some other confusions, all right? So I'm going to get my red, right? Now, as I said, you got to pick a bond that's close to the adjacent ring, which is this, as in the previous case. You can move up or below. I'm going to just move it up. And if I move this here, I'm going to move this here, and then I'm going to move this here. You cannot go into the next ring, okay? If you do that, you're never going to be able to reproduce and have resonance, right? So let's draw this. I think I picked a slightly offset blue. It's all right. It's still not red, so we're good. Okay, so let me go get my red, right? So that means these two are unaffected. This bond is now here. This bond has come here, and this bond's come here, and this stays wherever they were. So this is a resonance structure of this. Now, what if I want to do something else? Let me get a different color. Now, again, you want to move this bond into the next ring. You can only move one ring at a time. You cannot move them all at the same time, right? Now, let me go get my blue again. That means I'm going to redraw this. I'm drawing it a little smaller because of space constraint here. Now, I'm going to go get my pink. Now, these were undisturbed by this movement. These were undisturbed as well. Is this bond moved here, this bond moved here, and this bond moved here. So this is the resonance structure of this. This is the resonance structure of this. And we can go back exactly the opposite way. You can take this and move it here. You can essentially go back to where you started. It's just a long cycle. Okay, but I don't want you to do that. So, which means essentially we can produce resonance. So this is all three possible. So aromatic. So I'm not going to solve the third problem in lieu of time to keep the video less than 10 minutes. I highly recommend you try this at home and then get back to me in class with questions, right? So the next video, I'm going to show you something where I mentioned is a knowledge that you needed from your general chemistry coursework when you learn Lewis structures, right? So, and how knowing that knowledge is important to further understanding your idea of aromaticity is what we're going to look at the next video. Next video is also going to be crisp and short and up to the point. All right, so stay tuned.